All right. 2 classes ago, we did work. Make sure you know how to do work. I think that's honestly one of the more difficult parts of the unit because we have to bring back forces, and in that angle between displacement and the force can be kind of tricky. You may want to look up additional videos on that. You need to be able to calculate that angle fluently. It should be natural for you to figure out the angles. You can also come to tutorials. You need to email me if you want to come to tutorials if you're online. Say, hey, I want to come to tutorials sometime this week, and we'll set up a time for after school that I can hit you up on tutorials or during one of my conferences. With that, and then we also did energy last time. Again, energy should be the easiest part of the unit for you. It should be like quick. Obviously, algebra, not everybody's strong on their algebra. You need to practice your algebra to make sure you're good with it, but the physics of it shouldn't be too hard. All it is the equations, the kinetic energy equation, the potential energy equation, and the spring energy equation. So today we have something called the work energy theorem. It's just another equation, but it happens to be, we're not going to get super deep into it, but it happens to be a very deep equation. But here's what it is. It's simple. The net work done on an object is equal to the change in kinetic energy of that object. And so we're combining the last 2 days. We're combining this idea of net work, where we calculated all the work done on an object and then added them all together to get the net work. And that's equal to the change in kinetic energy of an object. And so we talked about kinetic energy last time. And so we should be able to calculate final minus initial kinetic energy. So if I give you two velocities, you should be able to do final minus initial, and you should be able to get the change in kinetic energy, and they should be equal to each other. Okay. Now we can expand this equation a little bit if we would like to. This is obviously messier, and this is not how I would love for you to memorize this formula, okay? But this is just the expanded, like the net work, right, is just the net force times delta x times cosine theta, right? Or, again, you can find net work the other way. You can find net work as summing up all the forces, or summing up all the works, of all the forces. And then change of kinetic energy, it happens to be 1/2 m final squared minus velocity initial squared. Okay. I will get many people that do this, that will do 1/2 mass times velocity final minus velocity initial squared. But that is not correct. This is bad. Okay. You need to be doing 1/2 m v final squared minus v initial squared. V final squared minus v initial squared is not equal to vf minus v naught all squared. Okay, those two things are not the same thing. If you do this, you would need to FOIL it, and so you would get vf squared minus 2vf v naught plus v naught squared. So hopefully you can see how those are not the same thing at all. Okay. If that's even more confusing for you, just go back to the idea of just what changes. It's k final minus k initial, and so really the expanded version of this right side is 1/2 mass v final squared minus 1/2 mass v initial squared. This is the more simple, the more easy to understand version of the work energy theorem, and so you might want to do that too. But all in all, this is the formula. So let's try it. We have a 600 kilogram car. It's going to brake from 32 meters per second to rest over 60 meters. And I want to know what the average force of the car is. Okay. And so I have this formula. The net force. Let's actually start from the beginning. Let's even go a step back from that. I know that the net work done on an object is equal to the change in kinetic energy of the object. If I see some sort of change in kinetic energy, if I see an initial velocity and a final velocity, then I know there's a change in kinetic energy which means I know that there's net work involved. And so if I'm looking for the force, I can use this to figure it out. I know that the net force times the distance covered times cosine theta is equal to my change in kinetic energy. So my 1/2 mv final squared minus 1/2 mv initial squared. Or I think the last slide I wrote a different version of it, essentially a grouped version of it. So we'll go ahead and use the one I wrote, mv final squared minus v initial squared. This one also works. Okay, we're looking for the force, so we're looking for the net force. Okay, we're looking for F net in this case. Because if we draw a free body diagram, you'd realize that, okay, friction is what's slowing down the car, normal's up, gravity's down. Okay, there's only one force that's really causing net force because these two are balanced. Therefore, the net force is the frictional force. That's what we're looking for. We're looking for the frictional force. We're looking for that average force on the car. We would know that our displacement is 60. Okay. And then cosine theta, well, what direction is my displacement? My displacement is to the right because I am still going forward. Even though I'm hitting the brakes and slowing down, I'm still moving forward. If you hit the brakes in your car while you're driving forward, you keep moving forward even though you're slowing down. So my displacement is to the right, but my force is to the left. Okay? And so that means that there's a total angle here of 180 degrees. And so I'm going to write in cosine 180. That's equal to 1/2 times the mass, 600, times v final squared. My final velocity is rest. My final velocity is 0. 0 squared is 0, so I'll leave it like that. Minus the initial squared is 32 squared. So we can rewrite this. F net times 60 times, what is cosine 180? Go ahead and put in your calculator. If you don't know, cosine 180, I get a -1. And then 1/2 is 600, that's 300. And then 0 minus 32 squared is just 32 squared. What is 32 squared? I don't know. Let's throw it in the calculator. -1024. Let's simplify this a little further. So F net times -60 is equal to, what's this, times 300, -307200. And let's divide that by 60. And so we get F net is equal to 5,120, and that is my final answer. So you can see it's just a long formula. There's a lot to it. There's a lot of algebra here. That's why we had to drill in a lot of kinetic energy. That's why there's more kinetic energy than anything else on that last worksheet. And that's why we had to drill in a whole day of just doing work, just calculating work over and over and over again. Same formula over and over and over again, because it's going to be used so much today's lecture. It's a very powerful formula. Let's see another one. We have a 5 kilogram box slides down a 5 meter ramp at an angle of 20 degrees. What is the final velocity if it started at rest? So let's draw a free body diagram real quick. We have a ramp. Let me draw it less steep. So like that. 20-degree angle in a box. And we'll assume it's frictionless. I didn't write it on here, but let's go ahead and assume it's frictionless. That's what I want for this example. FG and normal up. Okay. And so we want to find the final velocity. So let's go ahead and use this idea. W net equals delta K. So what is the net work? Well, it's the net force times delta x times cosine theta equals the change in kinetic energy, which is 1/2 m v final squared minus v initial squared. We're looking for final velocity, right? We're looking for VF, which means that we need everything else. So unfortunately, that means we need to find the net force, which can be kind of complicated. We had to go back to our slope notes But really, what we can do is we can just think about what is the force that's causing this box to go. On a slope, it's gravity that's causing the box to move. Gravity is doing the motion. If you remember this normal force right here, the work done by the normal force is 0. Okay? Do you remember that? That is perpendicular to the slope. This thing goes down the slope, normal's up, so that's a right angle right there. Therefore, the work done by the normal force is 0. And so, although we're not going to use all of FG because we're going to use a component of it, the cosine theta will do that work for us. And so on slope problems, we're just going to assume that the net force is F of G for now. This is giving me pain. Okay. So Fg times our distance is 5 times the angle between the force and the displacement. Well, the displacement is down the ramp and the force is straight down. So what's those? So I want to figure out this angle right here. Well, it's not 20 because this is the angle of 20. It's the other angle. If this is right angle, if that's 20, that means this is 70, right? 20 and 70 have to add up to 90 on a right triangle. And so we're going to use the angle 70 here. Okay? And it's equal to 1/2 m. V final squared is what we're looking for, minus V initial squared. Let me actually go ahead and plug in everything. Oh! My bad, I didn't mean to do that. Let me rewrite that down real quick. So F net delta x cosine theta equals 1/2 m V final squared minus V initial squared. And then we have F net was F of G, we said. Delta x is 5. Cosine of 70, we said, for that picture. And then 1/2 of 5. V final is what we're looking for. And then minus V naught. V naught, we started at rest, right? So V naught is just 0, so I'm just going to leave it like that. Because V naught is going to be 0, so that whole thing is going to be 0. Fg equals mg. And so Fg equals mg, which is equal to 5 times 9.8, which I believe is 49. So 49 times 5 times cosine 70 is equal to 1/2 times 5 times Vf squared. Let's do this. 49 times 5 times cosine 70. Okay, I got 83.8 here for that. And I'm going to double check I'm in degrees. I was in radians earlier today, but I am in degrees now. Great. So this should be good. And then 0.5 times 5 is equal to 2.5 Vf squared. So let's do 83.8. Let's actually just pull the number down from earlier so I can be more accurate. And then we're going to divide by 2.5. So Vf squared is equal to 33.51. And then we're going to take the square root of that answer, and we get Vf is 5.79 meters per second. All right. Let's do one more. A 3,100 kilogram rocket ship traveling in space starts its 5,300 Newton thrusters for a distance of 350 meters. If the spaceship finished its acceleration at 42 meters per second, what was its initial velocity? So again, we have a change in velocity, which means we have a change in kinetic energy, and then we have a force over a distance, which means we have work. If you ever see a force over a distance and you see a change in velocity, that means we're going to use the work energy theorem to relate them. If you see something about work, if you see something about force over a distance, that means there's work. If you see something about a change in velocity, that means there's a change in kinetic energy, so we can relate them. Therefore, the net force times the delta x times cosine theta is equal to 1/2 m V final squared minus V initial squared. Okay, well, what's the net force? To get that, let's do a free body diagram. Rocket ship traveling in space. There is no gravity. There's no normal. There's no surface or anything. It seems like the only force are the thrusters. And so that is my net force. My net force is the thruster force, which is, let's just go ahead and plug it in right now. Why not? It's 5,300. What's my displacement? Well, my displacement is 350. That's how far I travel. And my angle, what's my angle between the two? Well, my force is to the right and my displacement is to the right. Therefore, the angle between those two is 0. So cosine of 0 times 1/2 times my mass, which is 3,100 from up here, times my final velocity. It finished my acceleration at 42 meters per second, so my final velocity is 42. I'm looking for my initial velocity. Okay, so 5,300 times 350 times cosine of 0 gives me this number. And then 0.5 times 3100 gives me this number. 42 squared gives me 1764. So let's divide both sides by 1550. So that big number divided by 1550 is 1196.77. That's going to be equal to 1764 minus V naught squared. So let's subtract 1764 from both sides. And I'm left with negative 567.22 is equal to negative V naught squared. And so let's go ahead and multiply both sides by -1. So both sides are positive, and then we can just take the square root of both sides. And we get, V naught equals 23.8, which should make sense. It was less than our original velocity. So again, we were able to do these crazy problems with so much information from this pretty simple formula. It's a pretty powerful formula, and it turns out once you get to college and you take these more advanced physics courses, you can actually do even more with it. It's pretty powerful. It's pretty cool. You have to understand it. You have to be able to do kinetic energy. You have to be able to do networks. And so if you're still struggling with that, if you didn't fully grip the network thing, come to the tutorials, ask about the worksheet 1 so we can go over it together and I can help you understand it, okay? With that, I have nothing else to give you. Next time we're going to go over conservation energy. So that is all I have to say for today. Have a good day.